Okay, so let us see the remark that I was talking about in the last video. So this section ends with this remark, and it's about all the axioms that we have seen so far. So the remark is this. The axioms of set theory that we have introduced. That is, these axioms we have already seen from the first axiom through the 11th axiom. Excluding the dangerous axiom 3.8, which we know is the excuse me, axiom of universal specification, which leads to Russell's paradox. So this is not acceptable. And these axioms are known as the Zermelo-Fraenkel axioms of set theory. As you have probably guessed, these are the names of the mathematicians who introduced these axioms. They are named after Ernst Zermelo. And let me write the time period also, from 1871 to 1953. And Abraham Fraenkel. You can look them up on the web if you want. From 1891 to 1965. So they were almost contemporaries. Now, apart from these axioms, there is one further axiom. And that is the axiom of choice. That we will need. The famous axiom of choice. And we will see this in section 8.4. So in the 8th chapter we will see this. So we have we will see many things before we get to this axiom. It will be needed, but it will be needed much later. Okay. giving rise to or giving us, anyway, same thing, giving rise to the Zermelo-Fraenkel choice and the initials of these letters give us ZFC. So that's where this ZFC comes from, and it means Zermelo-Fraenkel choice axioms of set theory. Okay. But we will not need this axiom. This axiom means the last one, the choice axiom. Only much later we will need this. So with this remark, this section ends, the text part of this section ends. So after this we have the exercises. So let us now see the exercises. Okay, so here we go. The first one. Exercise 341. Let f from x to y be a bijective function and let f inverse from y to x be its inverse. Okay, so we know that bijective functions have inverses. In fact, they are the only functions which have inverses. Let phi be a subset of y. Okay, so we are also given a subset of the range of f. Prove that the forward image of phi under f inverse and or is the same set as the inverse image of phi under f. Thus, the fact that both sets are denoted by the same symbol, we have already seen that both of the sets are being denoted by this symbol, will not lead to any inconsistency. Okay, so let us now see how to solve this. It's not very difficult. So first of all, we try to understand what the question means. So we are given a function. So this is our set x, this is y, and we have a function f from x into y, and we also have a function, because f is bijective, we also have its inverse whose domain is y and range is x. Now we are given a subset v in y. So because v is a subset in y, we can find the inverse image of v under f. But at the same time, since f inverse is now also available to us, and v is a subset of the domain of f inverse, which is y, so we can also form the direct image or the forward image, which we are calling, of v under the function f inverse. Now we are being asked to show that these two sets are actually equal, and that's why this notation, which does not distinguish between these two, is justified. Okay, we won't have any inconsistency or any problem using the same notation for both the sets. So since we are going to show that the two things are equal, before showing that we have to denote them by, temporarily at least, by some two different notations. So let us do that first. Let us temporarily denote the forward image of v, under f inverse by f inverse v. It's just that same notation, but to emphasize the fact that it's the forward image of v under f inverse, we are going to put a subscript f. F stands for forward, and the inverse image of v under f by this. I stands for inverse. Okay, we have to show that these two sets are equal. So the usual procedure, we have to show that each of them is a subset of the other. So let us first show that this is a subset of this. So we assume an element in the first set. Okay, now what is this first set? It's the forward image of v under the function f inverse. Okay, so then x is equal to f inverse v for some element v belonging to v according to the definition of forward image. But now note that since f is a bijection, so x is equal to f inverse v if and only if v is equal to f of x. But this implies f of x is equal to v, and v belongs to v, so we can write that here. Okay, now you go to the definition of inverse image of a set under a function, in this case inverse image of v under the function f. An element belongs to that set if and only its f image belongs to the set, belongs to the inner set. So here the F image of X belongs to V. So that means X belongs to the inverse image of V. This gives us inverse image of V, but keep in mind we are denoting it by this symbol. So any element in this set has been proved to be also in this set. So this is a subset of this. Now we prove the converse. Next, let X prime be any element in the inverse image of V under F. Then, so in proving the converse, the arguments are going to be basically the same like this, what we have here, but in the reverse order. That's all. It's that straightforward. It only looks complicated. You should be able to see past these symbols, what they actually mean. Then, same thing, f of x belongs to V. Okay. So since f of x belongs to V, so this is x prime. So we can write a symbol for it. I mean, we can give it a name. Let V prime be f of x prime. We are calling f of x prime V prime because it's in the set V. So somehow that denotes the fact that it's from V. Then we can again use the fact that f is a bijection, so its inverse function exists. Then x prime belongs to f inverse of V prime. Okay. Now note this fact. See, V prime is in the set V. Okay. Now since V prime belongs to V, it's coming from here. Since V prime belongs to V, we have this is not belongs to, this is equal to. Sorry about that. We have f inverse of V prime belongs to f inverse of V, but what? The forward image. You see, what we are doing here is this. If we have a set, say we have a set A, and there is a function on some domain where A is a subset, and we have an element in this set, and let that function be G. Say G is from B to C, and A is a subset of B, and small a is an element in A. Then GA will be an element in this forward image, G of capital A. Now think of f inverse in place of G. So that's what we have written here, and that follows from this. So you think of V in place of A, V prime in place of small a, like that. Then you can conclude this. But since the forward image of V under f inverse, we are denoting it by this symbol. So that's why we have written that subscript f. Okay. So now what have we got? This implies, but what is f inverse of V prime? It is nothing but x prime. So this belongs to the forward image of V under f inverse. So any element in the inverse image of V under f is also in the forward image of V under f inverse. Thus we have this also as a subset of this. So they are equal. So whether we treat this set as the inverse image of V under F or the forward image of V under F inverse, it does not matter. They are the same set. So that's why we can drop these subscripts now and denote this set simply by this notation, which we have done, and now it is justified. Okay, so here the solution ends. So next we see the second one. So what this one says, let f from x to y be a function what from one set x, okay, from one set x to another set. I don't understand why we have to write this part from one set x to another set y, because once I write this notation, it's understood that f is a function from x into y, that is in particular that x and y are sets. So this much we need not write anyway. So next what, let S be a subset of x, I think, and U be a subset of y. Please excuse the lizards, okay, I can't help it, I don't want to kill anything, so you have to put up with this inconvenience. Right? What in general can you say about f inverse of f of s and s? Also, what about f of f inverse of u and u? Okay, so if you recall, in the previous video or in the previous videos, a few of them where we were discussing these images and inverse images, after defining these concepts we saw some examples, and there we calculated these things, and there we came to the conclusion that the forward image and inverse image, these two things don't quite invert each other. In fact, we wrote this, we mentioned this very line, that is, these two sets are not necessarily equal. Also, these two sets are not necessarily equal, but now we have to figure out what is the relationship between them. Okay, so let us, just like the previous exercise, for this one also let us draw a Venn diagram and see what is going on. So again we have x and y. Okay, but there is a big difference between the previous and this one. In the previous one, f, the function was bijective. Now f is not necessarily bijective. It may or may not be bijective. We don't have anything to do with f being bijective. So there is a function, any function. Now we are given a set S in X. S is a subset of X, and also a subset U of Y. Okay, so what happens when I apply F to S? We will see this U afterwards. Okay, once I apply F on S, I get the image, the forward image of S under F, and that is a subset of Y. On that, if I apply F inverse, then I come back to X. So now I have this subset F inverse of F of S. What is the relationship between this set and this set? That's what we have to figure out first of all. And similarly, if we start with U here, if we have U here, then we can take its inverse image, F inverse of U. On that we can apply F. So the forward image is this. What is the relationship between these two sets? There is a relationship, and it's not equality that we have already seen. In none of these cases we in general have equality. We have already seen in the examples, but now we will figure this out, the exact relation. So let us see the solution. And okay, I myself keep forgetting what the relationship is. Okay, so our first claim is this. We claim that S is a subset of this, F inverse of F of S, and equality occurs if F is injective. That means S is always a subset of this set. If you remember in the diagram that we draw just now, both these sets are subsets of X. But now we have to prove that S is a subset of this. And in this relationship, we will have equality if F is in particular one-to-one or injective. This is what we have to show first. So we take any element in S and we show that that also belongs to this set. So let X belong to S. Okay. Then F of X belongs to F of S. In solving this one, we have already seen how this is true. If X belongs to S, then by definition of F of S, Fx belongs to F of S. And this implies X belongs to F inverse of F of S. Think of F of S as a set. Say you think of this as some set A, and look at the definition of F inverse of A. This consists of those elements whose F images are in A. So it's an element whose F image is in A. So that means this element will be in F inverse of A. So that's why we have this. And that's what tells us that this relationship is true. Hence, S is a subset of this. Okay. Now we have to show that the reverse inclusion, that this is also a subset of this, will be true if f is injective. So that means we now have to assume that the function is injective. Next, assume f is injective. Okay, so now we want to show that this is a subset of this. So we start by assuming an element, considering an element in this. So let x prime be an element in f inverse of f of s. Since we have already gone through these arguments, I am now going to write some steps whose justifications you know already from this discussion. Then this implies f of x prime belongs to fs. Why? You know from the definition of f inverse of f of s. Think of this as a set and you get this. This implies fx prime is equal to fs for some s belonging to s. Now this is coming from the definition of the forward image of s. Any element in the forward image of s is f of some element in s. So in particular, this element is also f of some element in s, and that element we are writing as small s. Now we will use the fact that f is injective. Since f is injective, from this we have x prime is equal to s, because being injective, f will map, f cannot map two distinct elements onto the same element. This cannot be true if f is injective, because then f is not one to one, f is many to one. So that's why these two must also be the same. And that's how from injectivity of f we get x prime is equal to s, but s belongs to s. So see what we have achieved. Any element in this set is in s. So f inverse of f of s is also a subset of s. And combining this and this, we now have equality as we claimed. And we have s is equal to this. Okay, so this is the first claim, and it explores everything about this first situation. Now we go to the second one. Next, the second one is also similar to the first one, but there are differences. Next, we claim, now the opposite thing will happen. F of f inverse of u is a subset of u, and equality occurs if f is now surjective. Instead of being injective, we now require f to be surjective. that is onto. Now we have to prove this. Let x, y, x prime, all these things we have already taken. So let us take a, b, c. Let a be any element in f of f inverse of u. So that means a is an element in the forward image of this set under f. Then a is equal to f of b for some b belonging to f inverse of u. That is by the definition of the forward image. But now b belongs to the inverse image of u under f. So that means f of b will be in u. This implies f of